All right, everybody. Hello and welcome to this lecture on the chi-squared statistic. We saved the chi-squared statistic for last because it's a little bit unlike any other of the statistics that we have done, and let's talk about why. All right, it has kind of a fun name. It's not chi-square, it's chi-squared. It's another one of those Greek letters. We're surrounded by Greek letters in statistics. But what is a chi-squared test? A chi-squared test looks at only nominal or categorical variables, and it uses frequencies all the way back when we did frequency tables, you might remember. It uses frequencies, or the amount of individuals that fall into a certain category, for us to run analysis on. So when do we use it? We use it when we have nominal data, of course, and when our scores are frequencies, how often or how many occurrences we have of any given category. So what I have shown here is our funky little chi-squared distribution. So just like Z, T, F, R, we almost have like the whole alphabet, right? Chi has its own little distribution, right? And what it's assessing is if what we observe is what we would expect to see in terms of the total number of frequencies in each of these categories. So we'll start using these terms observed and expected, all right? Observed and expected. So it tells us that the frequencies we observed are what we expected. So before we even get into this, let's think about this very broadly. If we flip a coin 100 times, we would expect to see 50 heads and 50 tails. Doesn't mean that it's going to happen, but what we know about probability states that we should see about half, right, of each, because there are two options. So that's the general idea here, is that we will have some observed values given to us, and then we'll need to think about what we would have expected to happen given the variables that we have. So we'll take a couple different examples of this. Here's that funky little tail of the chi-square. This is another where there's no kind of positive or negative direction to our cutoff values that we'll be obtaining, because the chi-square is looking for something different, not if we're above or below a certain point, but if we are in fact seeing what we expected. So the math will sort of help us to explain this as well. All right, so we have a formula for the chi-squared statistic. It looks like this. Chi is like a funky big X. Right here it's just shown as capital X, but it has a little more flair on it. But the chi-squared statistic sums up all of our observed values minus our expected values squared over our expected values. So this is a little bit vague until we apply some specific ideas to it, but our observed and expected values will be dependent on what it is we're interested in investigating. So the chi-squared test is also interesting because there are two different forms of the chi-squared test. There's one that lets us assess the distribution of one categorical variable, which is called the goodness of fit test. And then there's also another type of chi-squared test, and they both use the same formula, strangely enough, but how we acquire the expected values is different. So here we look at the distribution of one nominal variable. We compare observed data to the expected data that we come up with. So again, we'll do an example of this in a moment that should help to clarify. The other type of chi-squared test is what we call the test for independence, which is when we look at two nominal or two categorical variables, and we use this to determine if there's a significant relationship between the two nominal variables, specifically if they are independent of each other or if they are dependent on each other, as this name suggests. So let's go ahead and just hop into it, right? As I like to do. I think these things are better done, than explained, though we do need a little bit of background before we hop into these. So let's go ahead and start with an example, all right? So let's say that we are interested in, all right, characters on cereal boxes, all right? We're interested in the distribution of male versus female characters, all right, characters on cereal boxes. This is actually an example from our book. I don't always pull straight from the book, but I think this is a particularly interesting example. It's comparing the gender of cereal box characters. And if we start to think about cereal boxes, I like to do this exercise when I talk about this in my classes, it's often hard for anybody to come up with a female cereal box character. And since this is a psychology class and this is linked to things like sociology, scientists will ask questions like, why? Why don't we have female characters on cereal boxes? Since cereal boxes are a medium that make it into many, many homes, right? So just sort of an interesting, but also kind of funny example, right? Not something we think about on the daily. So let's say that we're interested in knowing if there is an equal or unequal distribution of gender on these cereal boxes, and I'm afraid I kind of gave it away already, but let's go ahead and start writing this out. So we're going to look at gender. All right, so I'm creating a table right now, something called a contingency table. We use lots of tables in chi-squared. So we have gender, we have male, and we have female. All right, so I'm going to give us some observed values. So let's say that a researcher goes out and they get a big N. They have a lot of data. They have 1,386 cereal boxes that they investigate to see what the mascot or character on the box is. And what they observed was 996 male characters and 390 female characters. All right, so these are not equal, right? These are certainly not equal. But what we're going to do is test to see if the observed values equal what we expect within chance, or if they are different. So let's go ahead and take this time then to think about the hypotheses. I'm strangely going to put them down here. I usually like them up top, but they'll be okay over here. All right, so our null and alternative hypotheses. So we have kind of specific hypotheses for chi-squared tests. We're wondering if our observed values equal what we expect. That would be the null hypothesis, right? That there's nothing fishy going on here, but that our observed values will equal what we would expect. The alternative is the opposite of that, right? What we observed will not be equal to what we expected. And we'll go ahead and test this at an alpha of 0.05. All right, so we have observed values here, and how do we get expected values? So in this case, if the question was something like, we expect there to be an equal number of the genders, we would say take that N of 1386 and split it in two, right? If the genders were equally represented, we would have had 693 males and 693 females, okay? So for example, if you were to do a question like this on a quiz or on a homework, these values would be given. These might be given, but they might not be given, all right? If it's something like this where we're assuming an equal number, I might expect, all right, I might expect you to get the expected values for yourself, but sometimes they'll be provided. So let me know if you need clarification on that, but in this case, you would be finding these yourself. So let's go ahead and mark these in a couple different ways. So we have observed values here, we have expected values here. So if we think about the formula, all right, the chi-squared formula looks like this. All right, it's the sum of our observed minus our expected values squared all over our expected values, right? This is an E here. All right, so we have observed and expected values, and carrying on with our tables like we love to do, we could go ahead and get the difference, all right, the difference between these right now. So the difference would be the observed minus the expected value. So 996 minus 693, we get a difference value of 303. And then down here we get a difference value of negative 303. Imagine that, right? It's another kind of law of center, right? If this is going to be kind of the middle of our frequencies, we would expect an equal number above or below, or doing this difference score. All right, so this is our observed minus our expected. And then we could also take that value squared. That's what's going to be up in our numerator. All right, so we can take the difference squared. If we take 303 squared, we get 91,809. If we do it here, we get the very same thing, because remember, squaring a negative number will give you a positive number. All right, so this is just how the table can help us to fill in some of this information, but what we could also do is simply plug this into the formula, right? So we would take the observed for males minus the expected value for males squared all over the expected value. And then we would do the same for females. All right, 390 minus 693 squared all over 693. And we could do the math from here, all right? So what we're basically saying by this sum, or for this particular example, we're saying, okay, let's get the observed minus the expected values squared over the expected values for the males and for the females and add them together. So that's what we have done down here. So if we continue on with this math, we get something like, what do we get? We get something like 132.48 for this one, and imagine that the same for this one, because remember what we're ultimately doing is taking this difference value, which is what's right here, and dividing by the expected value. So it's really the same calculation. All right, so we end up with a chi-squared value equal to 264.96. All right, 264.96. All right, so we still need a critical value, right? But I just wanted to show you where all the data came from, right? Of course, we would normally get our critical value first, but let's go ahead and do that now. So this is the first step to our hypothesis test. The second is to grab our cutoff score. To grab our cutoff score, we need degrees of freedom, and degrees of freedom here is equal to k minus 1. We've seen K before, so degrees of freedom is equal to how many groups we have. We have 2 groups, right, male and female, minus 1. So we have 1 degree of freedom. 1 degree of freedom at an alpha of 0.05. So let's go ahead and take a look at our chi-squared table. If we have 1 degree of freedom at a significance level of 0.05, we're looking in that middle column of the significance levels, and we're on the first row. So we use a value like 3.841. Our chi-squared critical then is equal to 3.841. All right, so chi-squared critical equal to 3.841. All right, 3.841. So now if we think about our funky new little chi-squared distribution curve, let me go ahead and get a different color going here. So remember our tail, let's get a new slide here. Our chi-squared distribution looks something like this. It's a big long tail, all right? And anything out in this no man's land, anything out here in this critical region means that our observed values were not what we expected, all right? So our value of 264.96 is most certainly in this critical region, right? And in fact, it's like way, way out there, meaning that if we go back to our hypotheses, we would need to reject this. The observed values were not equal to what we expected. In fact, there was a very large discrepancy. Remember, we're always testing due to chance, but it doesn't seem like this discrepancy happened due to chance. It seems like male characters are more often on cereal boxes, not just because of the sample that we have here. So that's kind of a further explanation into our inferential statistics, right? We could grab another sample and see if the same thing is true, but based on this evidence, it's pretty compelling, right, that there does not seem to be an equal number of males and females on cereal boxes. All right, let's go ahead and try another example. Let's try an example where I give you the expected values, right? So let's say that we're interested in a certain region of the United States where they have a very different mineral content in their water from the rest of the United States, right? Different mineral content. So psychologists are interested in if that mineral content is shifting that region's average for mental health disorders compared to the national average. So let's say that we have, all right, so we have conditions, all right? So we have anxiety, we have alcohol, drug use, we have mood, we have or mood disorders, right? That includes things like depression, bipolar disorder, impulse disorders like OCD, ADD. and then none. All right, so let's say that we observe some values here. Let's say that we observe in our group that we're concerned about. These are the values for each of these reported types of disorders. Okay, and let's say that we expect, based on national average, considering how much data we have here, we would expect about this many of each of these disorders. So again, notice that these aren't identical, but they're also not entirely too far off, but they are different. So we beg the question, is there a difference in overall mental health in this group of people who are consuming different mineral content? So let's go ahead and start with hypotheses. All right, so we have our null hypothesis. All right, so are the observed values equal to the expected values? And then the alternative is, right, are they not equal? So let's give this a try at an alpha of 0.05. Let's go ahead and get our cutoff score first. So degrees of freedom is equal to k minus 1. In this case, how many groups do we have? We have 1, 2, 3, 4, 5. All right, so we're taking 5 minus 1 is equal to 4. So if we hop over to the table, we're looking at 4 degrees of freedom, so the fourth row, and we're looking at the 0.05 significance level. We find a value like 9.488. So our x, or our chi-squared critical, is equal to 9.488. All right, so let's go ahead and start to calculate this, all right? Because the calculation here is relatively simple. We could set up a table like we did before, but I'll go ahead and show you how we might do this by just plugging into our chi-squared formula. All right, so we have our observed minus our expected values squared over our expected values. So if we wanted to calculate this, it would look something like this. All right, so I'm taking the observed and the expected values for each of our groups. Now I'm on to this group here. Right, taking the differences, squaring them, and then dividing by our expected values. Okay, and then we get a sort of breakdown here. I'll go ahead and show you to this in a couple, show this to you in a couple parts here. All right, so -8 squared all over 146. So we can kind of see the steps here. So you could continue to do this in a table. It's a little bit different when each of our expected values are different. But it's up to you, whatever is easier on you. Okay, we have -7 squared over 536. And I'll go ahead and report these in decimals too right underneath here. So we have 0.44, we have 4.51, 1.54, 2.26, 0.09. And what do we get when we run through all of this math? We get a chi-squared value equal to 8.84. All right, 8.84. All right, and we needed to exceed a value of 9.488. So if we go ahead and think about this on a distribution here, this is not my prettiest distribution, but that's okay. Our critical value, all right, is 9.488. And if we're at 8.84, we're somewhere over here, right? We are not in the critical region. So if we are not in the critical region, we need to retain the null hypothesis, right? We would retain the null. And what does that mean for this particular scenario? Well, it means that what we observed in this specific region that has a different mineral content in their water, that they have an equal number of these psychological disorders that we would expect to see in any other area, which in this case would be good news, right? Especially if the scientists were worried about an increase in the disorders. So there we have an example of a goodness of fit. This is still a goodness of fit test in which the expected values are given to you and in which the expected values are not equal. All right, so we have one more chi-squared example that we need to get through, which is a chi-squared test of independence. All right, so hold on to your hats for this one. There's a lot of moving parts here, but it's still just systematic. So just kind of bear with, buckle down to kind of see what we do here, because it is an elegant little test in which we can determine if two categorical variables are independent of each other or dependent on each other. So we're going to go back to our cereal box example. All right, so we're going to have some observed values. Okay, so observed values of male and female characters, but we're going to add another dimension here. We're going to have characters that are children and characters that are adults, in addition to male and female characters, right? So let me go ahead and put this data in here, all right? So let's say that we're interested in knowing if there is a relationship between the gender and age of characters that are shown. So let me go ahead and put this data in here. We're also going to have total columns and rows. So I'm going to have total. I'm going to put some total values in here. So these totals mean this is the total for this column. All right, so if we add together 28 and 125, and then we have row totals as well. All right, and let's get a different color for our total. Let's say that we have 222 total in this particular data set. Okay, so we have something a little bit more complex now. A little bit more complex. We're working with two different sets of nominal variables, and one particular data point can belong to two of these categories, right? A mascot can be simultaneously male and a child. All right, so let's go ahead and get our hypotheses going before we get too far. All right, so hypotheses are a little bit different in this type of test in which we're comparing two different types of nominal variables. And they look something like this. The null hypothesis is that these two variables are independent of each other, meaning that they have no influence on each other. The alternative is that they are dependent on each other, that there's some way that these two variables interact which will impact how likely a character is to be one or two of these given categories. So what we want to know is if the proportions are the same given the total number of data that we have. So notice that we have more females, or more males rather, than we have females, right? So it wouldn't be fair for us to just say divide 222 by 4 and put them in each of these areas. It wouldn't quite work that way. So I'll show you what we need to do. So we'll test this at an alpha of 0.05. And before we move onward, let's go ahead and get our critical value. So remember, this is the first step of hypothesis testing. The second is getting our critical value. So we need degrees of freedom in order to get our critical value here. And we get them a certain way when we're working with an independence test for the chi-squared statistic. We take the number of rows we have -1 and the number of columns we have -1. Or you can think of this as simply how many categories we have in each of our two nominal variables. So for rows, we have 2 rows of data, children and adults. For columns, we have 2 columns of data, males and females. So this would look something like this, which is going to give us 1, right? 2 minus 1 gives us 1. So 1 times 1 is 1. So let's go ahead and hop over to the chi-squared table. All right, so we have 1 degree of freedom, and we're testing at an alpha level of 0.05. So we see a value like 3.841. All right, 3.841. So our chi-squared critical is equal to 3.841. That is what we are trying to beat in order to find statistical significance. Okay, so let's move into the sort of heavy lifting portion here. This is the tricky part. So observed values are reported, but expected values are not. So what we're going to do is calculate expected values. These values that we're about to calculate would be true if these variables are independent of each other, right? So how we get them is a little bit complex, but again, very systematic, and I think you'll get the hang of it after we just give it a little bit of practice. All right, so we have a new formula that we want to consider here. We have a formula to get expected frequency, so it's called F subscript E. And to do this, we need to get the frequency of the row that a certain value belongs to, as well as the frequency of a column that a certain value belongs to, all over n. All right, so what does that mean? And so we're about to get a little bit messy here, so just don't mind me. So we have an observed value here, all right? But let's say that we want to calculate an expected value for how many male children characters we would expect to see. Well, according to this formula, we need the frequency of the row that this particular score belongs to, which is 58, as well as the frequency of the column that this belongs to, which is 153, all over the total n. So that's exactly what we would do. We would go ahead and calculate this here over 222. And when we do this math, it's going to give us a value. This value is what we would expect if these two variables, right, age and gender, are independent of each other. So we're creating expected values that fit the null hypothesis. Then what we're going to do is calculate our chi-squared statistic as we would get a chi-squared value and compare it to our critical value. So just hang tight with me while I finish this up, and hopefully you'll start to see the pattern here. So here's our expected value for males who are children. Let's try for females who are children. All right, characters. So we have this total and this total. We're going to take 58 by 69, and we're going to put it all over 222, all right, the total value here. So what we're getting is proportions based on the totals of each of these groups. How many total males do we have? How many total females do we have? All right, so let's try one more time. Let's try for the male adult characters. This is the highest group, which we might have expected, right? So we're going to take the frequency of the column it belongs to and the frequency of the row. We're going to take 153. We're going to take 164, multiply them together, divide by 222, and we get something like 113.03. And let's try for the last one here. So for this value here, we need the frequency of the column times the frequency of the row. Of course, we've been using this 222 for each of these here. So we take 69 by 164 all over 222. Which is going to give us 50.97. Okay, so that took a little bit of work, right? A little bit of mental strain to get this all sorted out. But now what we have are 4 expected values that go with our 4 observed values. So now if we think about the chi-squared formula, right, we want to sum all of our observed minus expected values over our expected values. Well, we can do that now. So let's start with the first here. We have an observed value of 28 for male child characters, an observed value of 28, an expected value of 39.97. All right, so let's go ahead and plug that in here. We have 28 minus 39.97 squared all over 39.97. All right, let's go on to the next. Let's grab, I know the colors can be a little much, but I think it's helpful. Actually, why don't we keep up pink? Pink seems to stand out well enough. But now let's try for the next. All right, let's go ahead and try for female child characters. So 30 were observed, 18.03 were expected. So we have 30 minus 18.03 squared all over 18.03. All right, let's go on to the next. Let's try male adults. 125 observed, 113.03 expected. All right, 125 minus 113.03. We're a little squished here. We do want to get them all on one line for us here. And now let's try the last, adult female characters. So 39, all right, with an expected value of 50.97. All right, so 39 minus 50.97 squared all over 50.97. Okay, so a lot of work to get here, right? But now we're here and we're just running this like we would a normal chi-squared statistic. So what do we get? We get values like 3.55 plus 8 plus 1.25 plus 2.82. We get a value of 15.62. All right, chi-squared value of 15.62. We had a critical value, a chi-squared critical value of 3.841. All right, so if we go ahead and let's get a curve going here, 3.841 is the score we needed to beat for statistical significance. And I think we're there, right? If we have a score of 15.62, that certainly exceeds 3.841. So that means that we have a significant finding. That means that the null hypothesis has to go. We would reject the null. And we would suggest that there is a relationship, that the age of the character is dependent on the gender of the character or vice versa. Or basically that they are not independent of each other, that they do in fact have some influence on each other. Which shouldn't necessarily be a surprise given the first goodness of fit test that we did, that there was a clear difference in distribution of male and female characters. All right, so we'll be doing some more practice with this on one of our homework assignments, but as always, please be in touch if you have any questions on this material.